In this video, I want to talk about a phenomenon called beats. So this is related to interference of waves, but we're going to start describing what happens visually when you have two sets of two structures that have a certain periodicity. So let's say a set of lines at the top that you can see that the distance between the lines is marked there, and the lines at the bottom have a slightly bigger distance between the lines. So this is going to be equivalent or analogous to two waves with slightly different frequencies. So what happens when you superimpose, when you put one set of lines on top of the other one? So I'm going to select the bottom one and I'm going to move it to overlap the top one, like so. So let's see what happened. So as you can tell there, the set of lines they were aligned. The first lines on each set were aligned, but because the period of one was slightly smaller than the other one, they quickly fall out of line. They're not in step anymore. They're out of step. Then they are in step again, but then they fall out of step again. And then they're in step over here. They're out of step completely over here. In step, out of step, in step, out of step. So what happens here visually is a phenomenon called beats. So we have a pattern that repeats where we have the waves, as we just said, from here to here, they are back in step. And then all the way to here, they're back in step. And over here, they're back in step. So the certain amount of periodicity that gets superimposed on the periodicity that that these structures have. So overlapping them produces an additional periodicity in the system. More like this. All right, so let's take a look at what this implies for waves, for sound waves. So a sound wave, we have described it as a traveling sinusoidal wave. We're going to say that we have two sound waves, one described by the displacement d1 with a wave number k1 and an angular frequency omega1, and a second wave with a wave number k2 and angular frequency omega2. Now these two waves, we're going to assume that are traveling in a room and that your ear is located at x equals 0. So what you hear is going to be the superposition of wave number 1 and wave number 2. Now since our ear is at x equals 0, notice that we can cancel this term here because x is equal to 0 for both waves. And the displacement of our eardrum is going to be given by the superposition of d1 and d2, where d1 is going to be a sine of omega 1t and d2 is going to be a sine of omega 2t. Now what we're going to assume here is that omega 1 is different from omega 2, but they are similar. They are close, but they're not exactly the same. If that is the case, then the expression that we get for d1 plus d2 can be written in terms of these two frequencies here. We're going to define omega modulation, mod. Omega modulation is going to be 1/2 of omega 1 minus omega 2, and the omega average is going to be 1/2 of omega 1 plus omega 2. Well, I'll show you in a minute how these two frequencies play a role in the superposition of the two. But notice that omega modulation is a small number because omega 1 is close to omega 2. The difference is very small. And because the two omegas are similar, this number, the average omega, is a large number. At least compared to omega modulation, omega average is a large number. So again, the equivalent of what's happening here is the visual representation of the beats that I already show you. The waves, in terms of the waves that are coming to your ear, notice that these two waves have a frequency that is different. So even if we start with the waves synchronized here, because the frequency of the two waves is slightly different, eventually the two waves are going to be completely out of phase at some time later on, just like in the visual representation of those two sets of lines. We also have the same situation. The two sets of lines start in step, and then they fall out of step, and then they're in step again, and they fall out of step, in step, out of step, etc. So when we add omega 1, and not omega 1, d1, which is a sine of omega 1t, we add to that a sine of omega 2t, we can play some trigonometric tricks, and we can write the sum of those two trigonometric functions in terms of omega modulation and omega average. So the result that we get, I'm not going to show you the trigonometric steps, it's a little bit long, but the final answer is that the sum of the two, this is the displacement of your eardrum, is going to be 2a cosine of the omega modulation times time times the sine of the average omega times time. So what is this function look like? So notice that omega average is the sine function has a high frequency, so it's going to oscillate very quickly in time. And we have this very slow oscillating function given by 2a cosine of omega modulation times time. So this term there in the brackets is the amplitude. You can think of it as the amplitude of the sine of omega average times time, but it's an amplitude that is changing slowly with time. So what you end up having here is let me just show it without that line on top. What we end up having is a sine wave whose amplitude is modulated, periodically modulated. So we have this sine wave has like an envelope function. That envelope function is the function 2a cosine of omega modulation times time. So the envelope function changes with time slowly, and the inside function changes with time fast. So if you hear two sounds, as you saw in the previous video, if you hear two sounds, one with a frequency of 400 and the other one with a frequency of 404, the sound that you hear will have a frequency of 402, but the amplitude, that is how loud the sound is going to be perceived, the loudness of the sound is going to be changing with time. It's going to be sometimes soft when the two waves are out of sync, and it's going to be loud when the two waves are in step, in sync. And this pattern of soft and loud is going to be repeated with a frequency that we call the beat frequency, which is equal to the frequency of one sound minus the frequency of the other sound. This is what's called the beat frequency. All right, I just wanted to give you more detail, more than the previous video gave you about beat frequency, and I'll see you in the next one.